The programs that have used multiple functions up to this point usually had functions that called other functions. Now, so far we haven't seen any reason why it should not be possible for a function to call another copy of itself, a function calling itself. And that can indeed be done. And a function that calls itself is called a recursive function. In this section, I'm going to look at recursive functions. Now, syntactically, recursive functions are not different from any of the other functions we have seen so far. So the study of recursion is perhaps just as much a study of algorithms as it is of programming concepts. So there are a couple of classical examples that new students to programming usually look at when they study recursion. And we will do those examples in this section. Recursion can be a bit of a complex topic, but it's covered very well in this book. So I don't foresee you should have any problems understanding this. So recursion is not just covered in this chapter 5, but also makes appearances later on in chapters 8 and 12, and even in a place in the appendix. Now, ideally, when you call a function solves a problem for you and returns a result. And so far, that has been our understanding of what a function should be. However, sometimes the problem that you're trying to solve can be more complex, and you're not able to perhaps easily formulate a solution to the entire problem. But sometimes it is possible to divide a problem into smaller pieces. Can be slightly smaller problem, can be two equal sized problems. So there's really no restriction here on how that division happens. But you can divide a problem into a maybe slightly smaller problem. And if you knew the solution to one part, maybe to the larger part, you're able to come up with a solution to this slightly bigger problem. If you have an algorithm that works on this principle, you may be dealing with a recursive algorithm, with a recursive solution that can be formulated, can be built as a recursive function. The trick in all this is that the slightly smaller problem should essentially be, should resemble the original larger problem. Now this call to solve the slightly smaller problem using a call to the function itself, this is called the recursion step. Now at some place inside the recursive function, you must of course also have a return statement, because the idea is that once the problem starts becoming smaller and smaller and smaller, at some point the problem will become so small it will become trivial. At that point, a recursive function typically returns a solution. That solution goes back up, one step up to the calling function, which is then able to come up with a solution to this slightly bigger problem. And that's how recursion works. Now, all of this I realize may sound a little abstract at this point, but that's okay. Um, when you see a few of those examples, this should become quite clear. Um, so what we have to be careful about, however, is that we have to make sure that the recursion does terminate. Because if it doesn't, that would mean that the function keeps calling itself, keeps calling itself, keeps calling itself. And by now, we already know how the function call stack works. Each call to a function grows the size of the function call stack. If you keep calling a function infinitely without end, obviously your function call stack is going to grow too large and you're going to run out of memory. And so that is why it is essential that you know that at some point the problem will be small enough for trivial enough for the recursive function to return a result. And you should absolutely make sure that there's no way that somehow, for some input, your recursive function blows by that condition. This small trivial case, this small trivial version of the problem is called the base case. Now, any problem that you can formulate, that you can solve using a recursive algorithm can often, actually always, also be solved without, or non-recursively, without using recursion. However, recursion makes for a much more elegant and oftentimes more easily understandable solution. Let me give you a simple example, an example that is often given when you study recursion, and that is the algorithm to calculate the factorial of a number. N factorial is represented by n followed by an exclamation mark, and we read that not as n exclamation mark but as n factorial. What does n factorial mean? N factorial means n multiplied by n minus 1 times n minus 2 times n minus 3 times n minus 4, and these terms become smaller and smaller until we reach 1. N, of course, can only be an integer. Now, obviously, for 1 factorial, the factorial is 1. Not only that, one other thing that you have to remember, the factorial for 0 also exists and is also defined as 1. So this means if I were to ask you what is the factorial of 5, what is 5 factorial, the answer would be 5 times 4 times 3 times 2 times 1. If you calculate that, if you work out the product, the answer is 120. Now, the same thing could also be done using a simple for loop. And the code for that would be something like this. You initialize some variable factorial to 1, and after that you have a countdown loop which is initialized to the number whose factorial you're trying to compute, and you simply count down counter, and at each step each iteration in the for loop you multiply factorial by counter. By the time you exit the loop, factorial will contain the factorial of number. Now, there is one understanding of how to compute the factorial using a for loop. There is nothing recursive about that. But an alternative understanding is this. Now, recall n factorial is n times n minus 1 times n minus 2 times n minus 3 times 3, 2, 1. Now, if you look at this whole part over here, you could rewrite that as n times, and this whole thing is basically n minus 1 factorial. So, n's factorial can be defined as n multiplied by n factorial. This is a recursive definition of the factorial. The base case, well, n factorial can then in turn be defined as n minus 1 multiplied by n minus 2 factorial. And n minus 2 factorial can be defined as n minus 2 times n minus 3 factorial, and so on. So if I had a function that can compute the factorial, I might call that function for n to compute n factorial. And inside of that function, all I could do is just multiply n with, well, the factorial of n minus 1. And where do I get the factorial of n minus 1? By calling the same function again. By calling the function inside the function, but with a different argument. And inside of that, we'll be calling the factorial function again. Inside of that factorial, the factorial function again, all the way until we get to the bottom where we call the factorial for 1, and then we don't call the factorial function any longer, we just return the value 1. So, in a sense, for the example of 5 factorial, this is what you get. So unrolling the factorial using a loop would give you this expression over here, and you'd evaluate that. Defining 5 factorial, computing 5 factorial recursively would mean 5 multiplied by 4 factorial. Now we're going to look at an example in which we compute the factorials of multiple numbers. The type of variable we're going to use for that is going to be an unsigned long integer. Now that an unsigned long integer is the largest type of integer data type for positive numbers that we have available. Now you may be wondering, why are we using such a large variable type for storing the result? And the reason is that the factorial values of numbers grow really quickly. So what we're going to do in this example is we're going to build a function called factorial. If its argument is, if the argument it gets is 1, it returns the value 1, because, I'm saying this again, 1 factorial is 1. By the way, 0 factorial is also 1. It just is. Just have to remember that. But for anything else, for any arguments greater than 1, the function is going to return this. And you can see that in the expression that's being evaluated over here, the second term is a call to the factorial function. This is the recursive step. So let me just show you how this would work, how this program will work if we give it as an example. If you compute the factorial of 5, it would return the value of 5 times 4 factorial. Now 4 factorial will initiate another call to the factorial function, but with argument 4. This, since the argument is not 1, will return the result of 4 multiplied by 3 factorial. Now 3 factorial also causes a recursive call to the factorial function, which will return 3 times 2 factorial. 2 factorial again kicks off a call to the recursive call to the factorial function, which will return the value of 2 times 1 factorial. 1 factorial kicks off yet another recursive call to the factorial function, and since the argument now is just 1, which is our base case, this call to the factorial function returns the value 1. The value of 1 is returned for the call to factorial of 1. This finally allows us to complete this product, to compute this product, which is returned by this instance, this call to the factorial function, which happens to be 2. So 2 goes up. This completes the computation of this call to the factorial function, allows us to compute this whole product, which happens to be 6, which then goes up, and so on, and so on, and so on. And the final result is 120. This is now the code for this example program that we saw, and we're going to do something interesting over here. We're going to print out the factorials of, in this example, all integers from 0 to 21. Just 21. Now, if you think how can this possibly be? Why only 21? It's because when you go beyond 21, well, you'll have to check on your computer, but your computer will probably fail to compute the result because the result will be too large to keep in an unsigned long integer. So all we have in the main function over here is a for loop that goes 22 times from 0 to 21, and it prints out the factorial of the counter variable I, and prints it out over here, and then goes to the new line. So we have a /n character over here, and this is the recursive factorial function. And as you can see, it checks if the argument received is less than or equal to 1, and if it is, it returns a 1. This is the base case. If the argument is something larger than 1, and then in that case, it returns the value of whatever the argument number is, multiplied by the result, the return value, from a call to the factorial function. So we're calling factorial inside the factorial function. This is recursion. If you see any function, if you see any code in which a function is calling itself inside, means you have recursion happening. If you run this code, the output will look something like this. So 0 factorial 1, 1 factorial 1, 2 factorial 2, 3 factorial 6. So far, it looks like these numbers are not growing very fast. For 4, the answer is 24. For 5, we already saw the answer is 120. But after that, as you can see, the numbers start growing very quickly. And you can check how far your computer gets, if you can even get to 21, and how far you can get beyond that. So the first thing that the factorial function did was it tests whether the terminating condition, the condition that allows it to return a value, whether that has been reached. If not, a recursive call goes out somewhere further down in the function. Another new thing is the format specifier for an unsigned long integer. It's LLU, long U for unsigned integer. We already saw that in one of the previous tables where we listed all of the format specifiers, but here you have it. Here we're finally using it. Now, one of the things about C is that you cannot add your own data types larger than the native data types that come with C. That is something that you can do in some other languages like C++, which are for this reason called extensible languages. But yeah, so you can do that using a data structure called a class, but that is something that we're going to only touch upon at the end of this semester, at the end of this course. Now, one thing that can really make your recursive program that can really make it fail is if you forget to add a base case that returns a value. So don't forget the base case. Make sure make sure you write the recursion step right. Okay. Here's a second example that I want to show you. This one is called the Fibonacci series. That's a very famous series, and it starts with the numbers 0 and 1. That's all you have to remember. Every other number after that you can compute. Let me explain how. Each number is the sum of the previous two numbers in the series. So if you start at 0, 1, the next number is going to be the sum of 0 plus 1, which it is, 1. The next number after that is going to be the sum of the previous two numbers, in this case, 1 plus 1. The next one, 1 plus 2. Next one, 2 plus 3. Next one, 3 plus 5, and so on. Now, and that's it. That's how the Fibonacci series is defined. Now, as you keep going, the ratio of two successive numbers in the Fibonacci series starts getting closer and closer to this number, 1.618. It's kind of a famous number. This is called the golden ratio or the golden mean. For some reason, people have figured out that when dimensions of most things are in the ratio of 1 to 1.618, in this ratio, 1.618, humans tend to find that ratio aesthetically pleasing. And what examples do I mean by that? For example, the ratio of windows, the dimensions of rooms, length and width, the length and width of buildings, so all kinds of places. And people have also figured out that I think various lengths of the human body, like the ratio of the arm to, I don't know, to the height, things like that are also happen to be in most oftentimes around this ratio. Another example given over here is postcards. So the height and width ratio of postcards also happens to be like around the golden mean, 1.618. So that's just something on the side to know about the sequence. So we've seen that the base case for the Fibonacci series is the Fibonacci, the 0th and the first number in the Fibonacci series. Those we just have to kind of remember. Those are the values that have to be returned to us. Those are the base case. But for all other numbers, second, third, fourth, fifth, all the other numbers in the Fibonacci series are defined recursively. So the nth Fibonacci series is the sum of the n minus 1th and n minus 2th, n minus 2nd Fibonacci numbers. So they're defined recursively. And how do you compute the n minus 1st Fibonacci number? Well, you compute it by as Fibonacci number n minus 2 plus Fibonacci number n minus 3. And similarly, Fibonacci n minus 2 is also recursively defined as and computed by calling Fibonacci with argument n minus 3 and n minus 4. So you can see that the definition of the nth Fibonacci number in the sequence is recursive. And there's a corresponding program for that as well. So we have a main function over here. We have a function prototype for the recursive function Fibonacci. It takes an unsigned integer as argument and returns an unsigned long integer. This program asks the user for an integer, the sequence, the sequence number of the Fibonacci. So which Fibonacci number in the sequence you would like to know, you'd like to find. So the value is stored in an unsigned integer called number, and that is given as an argument to the Fibonacci function. And the result, in the main method at least, it looks like, after that is followed by a printf statement that simply prints out the value returned by the Fibonacci function. Simple enough. Simple enough. But what happens inside the Fibonacci function? Well, that is the recursive function we have. And over here we have, so Fibonacci function, if the argument given n is 0 or 1, it simply returns the value of n. For 0, it's 0. For 1, it's 1. But for all other arguments, it returns the sum of the return values of two recursive calls to the Fibonacci, to itself, to its own function. So if you run this with argument 0, the answer will be 0. If you run this with argument 1, the answer will be 1. If you enter integer 2, the answer will still be 1. For 3, you'll get 2. For 10, it's 55. For 20, 6,765. And so on. When you write the code for this, I really suggest following along and watching the function call stack and see how that grows. So remember, the call from main, that is not a recursive call. That's main calling the Fibonacci function. But Fibonacci calling the Fibonacci function, that is a recursive call. Those are recursive calls. Now you can also look at this graphically. So let's say you call Fibonacci for the number 3. You want the third number in the Fibonacci sequence. This will return the result of Fibonacci 2 plus Fibonacci 1. Fibonacci 2 itself will require two calls two recursive calls to the Fibonacci sequence with arguments 1 and 0. The call to Fibonacci with argument 1 will return a value 1. The call to Fibonacci with argument 0 will also return a value 0. And over here, the call to Fibonacci 1 will, of course, also return the value 1. But you can see how one function call here at the top resulted in 1, 2, 3, 4 other function calls. You can see this can grow very quickly. This is just for the argument 3. Now, when we call Fibonacci 3, one thing you have to remember is that it's really, you cannot count on, it is not predictable whether the Fibonacci 2 function or whether the Fibonacci 1 function will be evaluated first. You do not know. You cannot know. It's up to the compiler. Okay. So another thing about this second example of the Fibonacci series is that as the argument to the original call to the Fibonacci function from main, and then as those arguments become bigger, the total number of calls to recursive calls to the Fibonacci function, they do not grow linearly. They grow exponentially, and that's really dangerous. It means a definition, a recursive program whose number of function calls grows exponentially, that can really make your system run out of memory real quick. In this particular example, if the argument to the Fibonacci function is n, if you want the nth Fibonacci number in the sequence, that will produce roughly 2 to the power n calls, function calls, recursive function calls. So if you want only the 20th Fibonacci number, and if you compute that number recursively, that can translate into roughly 2 to the power 20 function calls. That is almost, actually that's a little more than 1,000,000. Check it out on your calculator. If you want the 30th Fibonacci number in the sequence, that'll mean approximately 2 to the power 30 function calls. That is 1 billion. Now you'll learn much more about algorithmic complexity in some other later courses, but let me just say that exponentially growing functions are like among the fastest growing functions. Functions that have factorial growth are even worse. However, what you must have also noticed is that the solution to finding the Fibonacci sequence is really quite elegant. And that's the other thing. Let me get to that in a minute. But this idea of a function calling itself, that is recursion, as you now know. The alternative to that is use iteration, and iteration means applying some kind of loop structure. Now, iteration also means that we're executing a certain number of instructions repeatedly, but iteration does not require repeated function calls. And that is what makes recursion so expensive. Even when function calls are not recursive, calling any function incurs quite an overhead. So while a recursive definition, a recursive solution to a problem is more elegant, it is performance-wise also more expensive. I want to reiterate one more time that have to be careful about not missing the base case, not blowing past the base case. I have to make sure that your code doesn't run until infinity. Now, if you make such a mistake in an iterative algorithm, no problem. The worst that'll happen is that you end up with an infinite loop. Now, this will probably not make you run out of memory, but if you blow by the base case condition, the condition that will finally return a value in a recursive function, that can be quite expensive and will cost you in terms of memory. So those are basically the negatives of recursive solution, recursive definitions, recursive solutions. The overhead is the possibly many number of function calls, which take memory, and besides memory, changing context, jumping from one function to another function, also costs you in terms of time. Remember that each recursive call to a function creates another copy of that function with its own set of local variables. And like I said, that can add up in terms of memory. Usually that is not the case in iterative solutions. Now here's a set of other, some of them actually quite famous examples of recursive algorithms in different chapters. I'll just point out some of the most famous ones. So there's factorial function, Fibonacci function, those we already did. The Towers of Hanoi, that's another one. Binary tree insert, maze traversal. Take a look also because some of these, selection sort, quick sort, sorting algorithms, printing trees, of course, yeah. So take a look at these because they might give you an idea for your semester project for what to do for that. Now, while we're talking about recursion versus iteration, using a recursive solution makes for good software engineering, makes for understandable code, makes for good code. However, there's a performance penalty. Usually, however, these days, compilers are able to perform a good amount of optimization, of code optimization. So usually these days, software engineering wins out over performance goals. Unless, of course, you are working in an area like gaming, for example, so game programming or real-time systems, even operating systems, embedded systems, uh, systems that are uh, resource constrained may value performance higher than good software engineering. But other than that, for all other cases, you oftentimes you may end up preferring um, the solution that offers a more that may offer slightly less performance, but makes for more easily understandable and more easily maintainable code.